I'm Ken. Nice to be up here. I'm a software engineer at Google, and I'm really excited to be working on Beam, which is, as my slide says, my slide doesn't say it, it's a programming model for streaming and batch big data processing, and it has particular features that help users control the balance between latency, completeness, and cost. And these are very significant and sort of at the core of this feature called triggers, which I'm going to talk about in some detail. So there might be different people here from last talk, so I'm going to ask the same question, like how many people here have heard of or used Beam and or Dataflow? Okay, that's cool. Okay, so this will be kind of familiar, and this particular slide, I'm going to focus on the fact that Apache Beam is unified. It teaches batch and streaming the same, and how you can get efficient data processing. I'm going to talk less about portability, but I'm going to talk about that just briefly to set the context. So I'll start by talking about big data. I know it's sort of, everybody here's talking about big data, but I'm just going to give a couple of examples to make sure that we're all on the same page, that we're talking about the same problems in big data. And then do some basics of the Beam programming model before I go on to watermarks and triggers, which are the main topics. So to set the context, I'm going to mostly talk in terms of streaming computations because that's where your data is infinite and out of order. But keep in mind, pretty much everything I'm going to say applies to batch processing as well, and they're unified in Beam. So I said that Beam is a unified model, but let's talk about a specific example of usage analytics. This is classic. Say you've got a mobile game, and you are keeping records of what all your users do. You've got data coming in from all around the world. You might process these as huge logs or as a stream of incoming data, or both. So here's your incoming massive flow of events. It's unbounded, which means you don't expect it to have any end. It might, but hopefully not for a long time. Assuming your game is prosperous. So what else can we say about this data? Well, your users are all over the world and they have flaky connections. So you're going to learn about these events from your users probably after they occur, sometimes long after. So let's look at 3 events that all occurred at 8 a.m. This event occurred at 8 a.m. and we learn about it almost immediately afterwards. The axis on the bottom here is when we receive the event. This user had a great connection. They're probably sitting on their home Wi-Fi or possibly their office Wi-Fi, which is usually more reliable. This user performed an action at 8 a.m. and we found out about it at 8:30. Right? This just means they were going through a tunnel or they were in kind of a dead zone for their cell network. And finally, here's an event that even though it happened at 8 a.m., we found out about it in the afternoon. This could be somebody who was on a camping trip or on an airplane flight, perfectly normal. So delays of a second, minute, hour, many hours, these are just a fact of life. So you do have this data source. There's nothing you can do about that, and you have this data coming at you, so what are you going to do? Well, you're going to take this unending stream of out-of-order data, and you're going to find a way to organize it into finite windows where answers are well-defined. So, for example, here I'm going to stick with this example for a while that you might want to compute results in fixed windows of 1 hour. So above you see the disorganized data, below you see these streams of an hour, or windows of an hour. Perhaps this slide, right, this is my straw man. I say, okay, now I've organized it into like windows of an hour and I've reduced the streaming problem to the batch problem and we're all good. But in fact, we have to get much more specific if we want to actually do this. Because again, we have data, it's coming in late. And part of that is that we don't actually know when we have all the data for an hour. Or, maybe you don't actually want to wait until you have all the data for an hour. How do you know when you have enough data to produce an actionable result? And implicit in that is how much compute power are you willing to throw at this? How much money are you willing to spend to get latency down? So let's focus on these dimensions of customization. These are from the subtitle of the talk, completeness, latency, and cost. Completeness means that the answer that you compute takes into account all of your data. Sometimes we can know when we have all the data, sometimes we can't. We can get closer and closer the more we're willing to wait. So latency then is how long you wait. How long do you wait to learn something from your data? At one extreme, you might want to wait until you're pretty sure you have it all. You might be waiting for a while. And at the other extreme, every time new data arrives, you might want a new answer immediately. The answer is going to be really tentative, so probably not very accurate, and it's going to be costly because you're going to be reprocessing a bunch of data. Some of your results are probably worthless by the time you even receive them. So let's look at some use cases and see where different applications come down on these dimensions. So here on the vertical axis, I've rated important and not important. It's a bit fuzzy, but this is just going to be a crude graph anyhow. And across the horizontal axis, I've put completeness, low latency, and low cost. So let's see what's important for different applications. If you're doing a monthly billing pipeline, then completeness is extremely important. It's sort of the spec for monthly billing that you wait until you have all the data for a month. So the blue bar is way up. It's all the way up at the top. Sort of also by definition, latency is not important. And so the red bar is very low. And that means that low latency is not important. It doesn't mean that latency has to be low, just noting the inversion there. And the green bar for low cost is also very small because it's not like you can cut corners when you're about to bill your customers. It's not a high priority. But say we wanted to give users a running estimate so that there's not a surprise at the end of the month when their bill is huge. Well, all the bars change a little bit. The blue bar for completeness comes down a little bit because we're probably comfortable with slightly less than complete data, and we certainly want to give outputs without utterly complete data, but even if it's not up to the minute that they query, that's fine. Low latency now becomes our primary priority, right? It's the definition of this use case that we get latency down to at least sub-month, preferably real time. And low cost now is a bit more important. So the green bar is a bit higher because we do want to keep costs down because this is not an authoritative bill that we're sending to somebody. It's just sort of so that they can see what might happen in the future with their bill. So these two use cases are actually computing the same result. But due to their goals, they differ in how they want to balance these three dimensions. We really want to separate concerns so that we can use one pipeline, the same programming logic, to address both use cases. And now, in a different domain, not a different domain, but a different application of possibly the same events, we could be attempting to identify users who are abusing or fraudulent. And here, we're probably using a heuristic anyway. So more data, getting really complete data is not particularly important. You're probably going to have kind of a converged model of a fraudulent user long before you have all the data. So the blue bar for completeness is really low. However, low latency is extremely important because every fraudulent activity that you prevent saves you money. And low cost is less of a priority because you're going to save money by succeeding at preventing fraud. So we're not going to prioritize low cost. So having talked about those trade-offs, we've got these three use cases. You can think about your use case, and you probably have the moment where you think, I have all these systems available. Which one am I going to use? This isn't nearly all the systems around. I'm not trying to be fair, accurate, or comprehensive. It just illustrates how lucky you are that you have tons of choices. You can address a lot of use cases and a lot of different performance considerations through choice of system. But which one are you going to choose? Well, I am here to give the same answer twice. I'm going to say you got to choose Beam because it allows you to express all of the different use cases using a single programming model. And I also think you choose Beam because you're going to run it on your backend system of choice so that your operational scenario is the one that you've chosen. If you want to hear more about these advances, at the bottom here I've plugged Tyler's talk. It's happening tomorrow. It's a great talk sort of about the advances of the system to the current state of the art. So let's move on to Beam itself and why Beam is a great choice for all these applications. We're going to step through the high-level aspects of the Beam model, and at the end you should have a sense of how the model addresses the variety of use cases before we dig into the specific feature of triggers. So the highest level of Beam will be familiar to anybody who's used Apache Spark, Flink, Google Cloud Dataflow, Crunch, Apex, Gearpump. There's a plethora of similar systems. In Beam, you structure your computation as a graph of transformations, which we call a pipeline. These squares here are p-transforms. That's a massively parallel computation happening across your data. And the arrows between the transforms are your actual data being transmitted. We call those p-collections. And the P collection can be bounded or unbounded, and those terms mean if it's bounded, we know it's finite. And if it's unbounded, it might be finite, might be infinite, we don't know. It's often simple to think of an unbounded P collection as a stream, but I'll try to stick to this terminology. Because we recognized a convergence of programming models between these major data processing systems, when Google created Cloud Dataflow, from the start we actually open sourced the Dataflow SDK, and later we donated all the code to Apache, and Beam began incubating as an Apache project. So the vision of Beam is to allow you to write a pipeline in your language of choice. Here is actual Beam Java and Python code. These are both in the repository right now. And the SDK for your language translates it into a language-independent representation. For the purpose of my talk, a language-independent representation is drawings of boxes and arrows. And then you take this pipeline and you run it on the service of your choice. The Beam repository currently has runners for Flink, Spark, Google Cloud Dataflow. Apache Gear Pump is on a feature branch. It's under development. And an Apex runner is under code review right now. So it's really moving along. This is sort of the vision. We're not 100% there yet, but this is what we're incubating to achieve. So let's walk through, just to make it super concrete and show that this is something that you're familiar with, even though a lot of people here seem to be familiar already. But we'll walk through this example of Beam Java code really quick. This is the word count, sort of hello world of big data processing. So first, we use a text.io read transform to read the works of Shakespeare from Google Cloud Storage. And then we use flat map elements to split all the lines on sort of non-alphabetic characters. We eliminate any of the empty strings we've created. We apply a count per element transform to gather up our word counts, use map elements to format them, and then we write them to some sharded text file. It's a dead simple pipeline, and the thing I want to point out is the last line where we haven't actually said how we're going to run it. You can, via just command line arguments or a little bit of prelude in your Java main program, run it on any of the backends that I mentioned. So when you sit down to write a program like that in Beam, you don't think about the underlying service. You think about these 4 questions. First, you determine what you want to compute at a very high level. If you're adding up scores for users, you're going to be computing a sum. If you are trying to compute or trying to do some like abuse detection, you're probably going to be computing a model of an abusive user. And then you think about where is your data in event time? Where is it distributed in time as the user experienced it? Such as, and how you're interested in viewing it, such as fixed windows of an hour or continuous user sessions. Or maybe you're processing not necessarily events per se, so you're sort of happy having them all in one global window. Is fine too, although obviously there's some limitations to that. And then, now that you've got your data organized into the windows, which I sort of illustrated earlier, when do you actually want to find out when those results are ready? That's the main subject of this talk. Do you want to wait until you have all the data? Do you want early results? Do you want late results? If some data comes in after we thought we had all the data? And finally, if your answer to that question indicates that you want repeated updates, how do those repeated updates relate to each other? How do downstream transforms and sinks need to kind of react to new data? So let's walk through these. First, I'll talk about what you're computing. This is the basic reading, transformation, aggregation, and writing of your data. I'm going to illustrate with just a single aggregation, the sum per user. So we have our mobile game, and we say, I want to compute the sum per user. I'm not talking about time just yet. So we already know basically what that entails for bounded data. This is what it looks like to write sum per key and write it to BigQuery. So if you can see, you've got your events trickling down from above, and the sum per key organizes it per key, which is represented by the color, and then adds them up. It's simple enough, right? It's one of the basic types of aggregation transforms in Beam. It's a grouping transformation. You can do a combine per key, which is similar to reduce from the MapReduce model. And prior to that grouping, you're probably going to massage your data a little bit, and so you'll do that with a pardo, which is sort of an extended flat map. That's very similar to the map from MapReduce. And then finally, a thing that we've added to Beam because we want it to be a proper programming model where you can build abstractions is composite transformations. You can take any subgraph and package it up as a transform. So when we return to the example of the grouping transformation, taking the sum per key, I want to point out that this is really interesting when your data is infinite. The code on the left isn't actually nearly enough to necessarily do anything with an incoming stream of data, right? Sum is not even well defined on an infinite set, say, of integers. And in general, it's likely not to converge, or it's not going to do what you want. We need to choose finite windows so that we can say that this sum actually has a meaning. So where in event time is your input distributed? What kind of finite bounded windows make sense for you? The question of where is all about defining at a really high level these nicely organized boxes from the stream below. We stick with the mobile game theme. This is a slide you've seen before. We have data coming in. It's out of order, but we're just talking about sort of defining platonically what we want to do. And in order to sort of talk about what that means, we're going to take a little diversion into processing time and event time. So here I've drawn a completely incorrect notion of time. Every purple square represents some event occurring in your system. I've drawn a yellow arrow for event time and a blue arrow for processing time. I've drawn them together, which would be how the world worked if we could instantaneously process all data and conclude some result from it, right? The real world doesn't work this way. Even Star Trek doesn't work this way. So we can't just think of time as being the same. We need to separate them. Event time and processing time are orthogonal here. So now I've separated the arrows. The horizontal axis is event time. I seem to have lost the label, but that's what's across the bottom there. And then processing time is on the blue vertical axis. The diagonal black line is that perfect world where processing time and event time are equal. I've drawn some squares on the line just to indicate that this can't really happen. Our data is not going to fall on the real-time line. It's going to be a little bit above the line. And the distance above the line is the processing delay. It's how long between the moment it happened and the moment that we processed it. So here's a sort of realistic distribution of data. Most of your data falls pretty close to the real-time line, and there's some event that's very delayed. So you can generally expect your data in a system like this to, a large bulk of your data is going to be close to the real-time line. Let's talk about organizing these elements into fixed windows of 1 hour. One really naive approach is to just spin up a pipeline and say output our aggregation so far for every hour that our pipeline's running, sort of micro-batching. Well, here's those processing time windows that I've just described. Every horizontal band of color is an hour of processing time. But each hour of event time, as your users experienced it, is denoted by one of these vertical lines, right? So the first hour, this orange bar at the bottom of processing time, it actually misses a couple of the events above it that are from the first hour of event time. And then the second hour of processing time contains events from both hours of event time, right? So processing time windows aren't based on the data, and they can't tell you. If you want to know what your users are doing, they can't tell you. But they're, of course, important to us. They are time as we experience it, right? So a lot of people think, I gotta get these processing time windows so that I can get some output at the end of every hour. And I'm here to say that triggers are actually the way that you should do that. So these are event time windows. I'm just gonna redraw it like that. These are the windows that we're gonna talk about. An actual hours experienced by your user is one of these vertical regions. It's just sort of sensible. No matter how long your processing time delay is, it's not gonna cross a window boundary, right? Your element falls in this window no matter what. And when you talk about windowing in the Beam APIs, this is what I mean. Now, if you really want processing time windows, it's actually really easy to achieve them because you can finagle the timestamps in Beam. You just throw away your data or your metadata, and you push all the elements onto this real-time line. It actually represents a different event. This is the event, the datum that describes when we found out about it. It's a reasonable thing. It's just not what you probably want. So with that diversion, here's my illustration of what windowing looks like in Beam with some real code. This will define fixed windows 1 hour, sum per key per window, and write it into BigQuery. So you see the kind of disorganized data at the top, the window into a transform, put them in these nice blue boxes, and then sum per key adds them up. Of course, let's see. Let's just move on. I want to point out that these windows, this fixed windows that I've said, you might think that I'm showing you some primitive magic that the Beam runner underlying it has to do, but that's not the case. Fixed windows, sliding windows, and contiguous user sessions, they all ship with Beam, but they're all just user-defined functions. You can write your own by kind of placing elements into windows and merging them. I think that's a particularly elegant part of Beam. So now we have everything we need to window this unbounded stream, right? Well, of course, we know that eventually we're going to see 1 row per user per hour if everything goes well. So windowing expresses actually how we want to partition our infinite stream in sort of, but it doesn't actually say what we are going to do with that partitioning. It doesn't say exactly what moment am I going to write that row? When am I ready to write some data into BigQuery? And that brings us to the final topic. When do you want those results produced? There are 2 pieces of the question, watermarks and triggers. If you saw Slava's talk just prior, that was a great deep dive into how watermarks work and how they're implemented. I'm going to talk about it at sort of a much higher level and talk more about how it integrates with the other features of Beam, specifically triggers. So here is my illustration of windowing at event time, right? The vertical bands of color, they extend forever upwards. That's the thing about them. We've expressed our computations in terms of the entirety of the contents of these infinite vertical bands. We haven't isolated anything finite. So in sort of mundane terms, we have a situation where we have to store all past data and we have to wait forever. We can't do that. So what are we going to do? Well, one easy thing to do would be to have a cutoff. We just say, after this fixed delay, any elements that come in, I'm going to throw away. It truncates the tops of each band, so we have this allowed delay, and we're not going to have to wait forever. And it also cuts off the number of bands I'm dealing with simultaneously, so I won't have to store an unlimited amount of data, but it's unfortunately kind of insensitive to our data. It's just like a bad watermark. A good watermark would be if we could take that straight line and just kind of squiggle it around our data. And we don't usually think of this as a curve, although I'm a fan of it. What we think of it as is as processing time proceeds upwards, that's us living our lives, our estimate of how far along we've progressed in event time moves to the right, but not necessarily linearly. So yeah, that's about it. For some sources of data, you can have a pretty near perfect watermark if you have, say, bounded sorted logs. For unbounded data, it generally can't really be perfect, and you have to use heuristics that are specific to the source, and that's what Slava's talk was about. These heuristics are very, very good. But let's see how they look on this kind of an illustration. Here, I've faded everything out. I'm about to start processing by bringing these into being as processing time moves upwards. So here, I advanced processing time a little bit. We've got 3 elements. The darker purple squares have arrived in a couple of different windows, so you see they're separately buffered appropriately for those 2 windows. And the watermark has barely advanced at all. It correctly predicts that we are going to see more data in the first window. If I advance processing time up a little more, then suddenly the watermark just shoots off to the right? And it concludes, this first window, this orange window is complete. We've got all the data. That's what that motion means. And then if I wait a little bit longer, the watermark kind of curves around and it concludes that the second window is complete, this blue window. The element that we haven't received yet, that's late data. If data comes in behind the watermark, that's just what we call it. We call it late. So when the watermark moved through the orange window, you could actually say it was a little slow. It would have been safe for it to move to the right even faster. The moment it got that second element, it could have concluded the first window was done. Whereas for the second window, it moved too fast. To some, it's up to your interpretation whether it's too fast, but it did cause some data to be classified as late. So that gives us a measure of completeness, but it's not the whole story. What the watermark is all about is it gives you this blue bar can go all the way up. The watermark tells you when you've got that completeness so that you can emit your monthly bill. But it does not allow us to address the use case of wanting a running total or sort of real-time abuse detection. Or, you can think of many other low latency use cases. So the full solution is triggering. I'm going to go into a lot of detail, so I've given up on cleverly illustrating this. This is the actual Beam code. This is the final draft. You can go run this. And what this says is that for fixed windows of an hour, after the watermark concludes the window is complete, write that sum per key into BigQuery. This is all you need. This is also the default behavior. It's equivalent to the default behavior, so you don't have to specify this if this is what you want. So let's walk through how this actually executes on an example. Here's a different distribution of events than last time. Processing hasn't begun again. Across the top, I've written the Java name for this trigger. So if I advance processing time a little bit, the watermark waits a while and then progresses through the first window, and the watermark concludes that this first window is complete, and we receive one output, an aggregation accounting for the one element that's been received in that window. Note, of course, the second element was in the second window, so it's not included in this aggregation. After a bit more time, the watermark advances through the second window, concludes it's complete, and outputs an aggregation for those three elements. The element that didn't arrive in time, that was after the watermark, is late, and by default, late data is dropped. You can configure this. So stepping back and kind of looking at this trigger and how it relates to the topic of the talk, how does it fall on these different dimensions? It's high completeness, as I talked about. It lets you know when you think you've got all the data. It's potentially very high latency because it waits about as long as possible, and it's low cost. And this, if you get 1 million elements in these windows instead of 3, that's going to be the same cost. I mean, the same cost downstream, right? The same number of aggregates emitted. So let's look at a trigger that trades off cost for latency and completeness. Here is a trigger that repeatedly, whenever you have at least 2 elements buffered, is ready to fire, and a different distribution of data. So let's move processing time a little bit up. 3 elements arrive, and since 2 of them arrived in the second window, it outputs an aggregation accounting for those 2 elements. I haven't even drawn the watermark because this trigger doesn't care about it at all. Oh, I have. Sorry, I thought I hadn't. Great, you're gonna get to watch the watermark move just a little bit. Then the element in the first window is still waiting for a second element to arrive. So some processing time advances, second element arrives, and we output an aggregation for that first window for those 2 elements. After a bit more time, another 2 elements in the second window and another output. So this is how this trigger proceeds. One thing I like to note is that there's no ordering implied by this kind of trigger, right? The second window fires first. So if you think of windowing and triggering as somehow like sorting your data and giving you chunks of it in order, that's not the case. So this trigger, it's low completeness. It ignores the watermark entirely. The watermark had barely moved at all. It's low latency, depending on your data. Every time you get 2 elements, you're gonna see some output. Note that in reality, maybe you'd use 1,000 elements, right? It's up to you, but 2 is just a good number for the slide. It's potentially really expensive because you haven't reduced your data very much, even though you're aggregating, right? The output is generally gonna be proportional to the input size. So let's, going from there, those are sort of 2 basic triggers. I'm gonna go to a very involved, but I hope actually fairly readable compound trigger to demonstrate how you can use this language of triggers in Beam to really express the details of your use case. So here I have the after watermark past end of window trigger, which is the same one I used for my first example. This is like your monthly billing. So if you wanted to output something and emit a bill, this is what you'd use. But in addition to that, I've added this trigger that I'm gonna paraphrase as when data arrives, wait 1 minute, then output. I feel like reading Java on stage is not good style. But then in addition to those kind of early speculative firings that will give you this real-time estimates for users, I've added that after any element arrives late, immediately update your answer. Let's see how this evolves for just 1 window. So again, let's start it up. Processing time moves up a tiny bit. We get 2 elements in the first window. The watermark correctly surmises that there's gonna be more data. But 1 minute after those elements arrived, we emit a speculative aggregation for them. So I'm gonna pause here. This kind of trigger has a different trade-off. It's low completeness, right, because it's ignoring the watermark. It's low latency, as low as you want. You set sort of the timeout here. And it's also low cost because you can get 1 billion elements in that 1 minute of timeout and it's only going to emit one aggregation. So this is kind of a cool trade-off. Might be what you want, especially if you're driving a UI. After a little while longer, the watermark advances, and it concludes that the window is complete, and we emit a second aggregation that takes into account all three of these elements. This emission, this aggregate that's emitted is it's specially labeled because the watermark says you think you've got all the data. So this is your on-time aggregation. And so you can use this downstream to send out your bill. And then long after the watermark is moving on to different windows, we get this late output, but assuming we've configured our allowed lateness to be a bit higher, it comes in and we just immediately emit a revision. So this compound trigger is it's an illustration of how there's a variety of use cases that you might want, and also even different behaviors as your data evolves for one application. And just that Beam kind of provides this language of combinators that allows you to express just what you need. Just to highlight this, this slide you might find, if anybody's looking at this on the internet, these are going to be out of date possibly, because that's how slides work. But this is just a sample of what you've got. You can take a bunch of triggers and wait till all of them are ready. You can take a bunch of triggers and fire whenever any of them is ready. You can repeat them, you can sequence them, and have demonstrated the watermark-based triggers and count-based triggers and processing timer-based triggers. So I didn't talk about now, really quick, I'm gonna talk about the accumulation mode, which is how do these refinements relate, which is that I've got a trigger, it's gonna output a bunch of revisions for the output per window, and then downstream I need to know what to do with those. And in Beam currently there's two supported, and they are discarding mode and accumulating mode. And the way to basically think about these is downstream, do I wanna emit a bunch of little deltas that something downstream is going to have to then re-aggregate and do the right thing with, or do you wanna just re-emit a revised total answer? Those are these two choices. They have different performance characteristics and different implications for downstream responsibilities. So to illustrate then, let's say I've got a bunch of data comes in and they both emit their first aggregation, which is 5. When some more data comes in, the diff, sort of the new aggregate for all this new data, the new sum is 2. And in discarding mode, we've forgotten about the 5. We fire and forget, and then we just emit this new delta of 2. But in accumulating fired panes, we've hung on to the 5. We add the 2 to that, and we output 7. So seeing this evolve, I mean, hopefully the pattern's pretty obvious. I just want to narrate it to make sure that I've emphasized enough times. On the bottom, you see like kind of the sums just increasing, and I'm outputting a replacement for the prior value. And across the top, I'm outputting deltas. So that's it. That's how triggers and accumulation mode combine to let you express your use case. And this is the tagline. This is that they give you control. The important thing is not that our system has some way of managing this. It's that you control this balance because this has to do with your application. This isn't a property of the computation. I should have said it gives you control over the balance between completeness, latency, and cost, just to hammer it home. And that's it. I just remember also the questions of the Beam model that let you tackle this big data that's out of order and unbounded. And just remember to think about what you're computing, where it is in event time, when you want to learn from it, and how you want to manage transmitting that data. All right, any questions? Sorry, I inserted this. I'm plugging people. I'm plugging Slava, who just talked, so you can't go see it. But I'm also plugging Tyler, who is going to talk tomorrow, and it's always a good time. It's really a fascinating sort of romp through the advances in data processing. And I hope this has at least inspired you to go check out Beam, join the user mailing list, join the dev mailing list, follow Apache Beam on Twitter. And if you really want to dig deep on just these topics, Tyler Akudau actually wrote Streaming 101 and 102, which are O'Reilly posts. And then Data Artisans and Google have each written these motivating blog posts about why you should use Apache Beam. And in case you're unfamiliar, Data Artisans are a company that employs a lot of Flink committers. Okay, and of course, at the bottom here, Cloud Dataflow is a Beam runner. You can run your Beam programs on Cloud Dataflow, and you should. You should give it a shot. Okay, and So that is it. Yeah.
Is it possible to trigger based on changes in the state of the window? Like, let's say if a sum of the element and changes in the 20%.
That's an interesting. I've received this question on Stack Overflow. You can find me there answering a lot of questions like this. And right now, there's not a straightforward way to do that. I think it's a really valuable thing. Just to repeat this in case anybody didn't hear, you asked if there's a way to trigger based on sort of a threshold of difference in the aggregation. And I think that there are other ways of expressing that in Beam, but not as a simple trigger. I'll talk to you over here first.
Handle with late data, sometimes you may need to have a lot of state that's stored, right? Does Beam provide anything to handle the large state? Or is it the responsibility of the other?
So Beam, there are many answers to this, and it depends on your use case. The question was, how does Beam allow you to handle large state? And one answer is that the runner, like Beam has an upcoming feature to let you express kind of little state machines, and then the runner determines how that state is stored. So the runner can do that. The other answer is that a lot of things you might do with state, you don't do with state in Beam, because Beam is sort of a higher level programming model, right? You might think you're aggregating, right, and maintaining an aggregator in state, and that's actually not what you would express that in Beam. Is you say, just do this aggregation over the whole P collection, and Beam manages the state under the hood, things like that. But if you really need state, then it's coming, and it's up to the runner. Okay, Jesse.
Could you talk about how the refinements are stored underneath? I think that's his question.
How the refinements are stored underneath.
So you're sending deltas sometimes.
Mm-hmm.
You're sending, here is the exact local.
Right. Oh, so those are stored in the same mechanism that a user is going to have available to them. So say you're doing a sum, and if you set it to discarding mode, it's not storing anything. It's just fires down the diff, and so in some sense, there's no state to speak of. If you're in accumulating mode, it's keeping one integer. But I think depending on what it is that you're aggregating, it's going to be storing one accumulator. Yeah. Yeah. So I mean, it will be one per key. Yeah. Per window. One per key per window. Yeah.
And those are in memory or on disk?
That's up to the runner. Yeah. Oh, sorry. And the question is, are they stored in memory or on disk? And that is up to the runner. Yeah. Yes, back here.
So since this is abstraction, you're creating a contract that's supposed to be usable across all of these different locations.
Mm-hmm.
And doing so, you're kind of trying to keep the lowest common denominator active across all of these.
I love this question. So the question is, we're creating an abstraction that's supposed to be runnable across all the backends, and so we're keeping the lowest common denominator, ? And we totally don't want to do that. That is not, this actually came straight out of the data flow model, and what we're doing is on the website, we're trying to keep the highest bar and then keep a matrix of what different runners support. So you should go check out the Beam website. We actually do have matrices, like this runner has processing time triggers, this runner supports streaming side inputs. So that's, the answer is definitely not, because I kind of think that would have a disappointing result.
Is there, who's maintaining? Like, is this a community maintained version, or is this still kind of like a Google maintained version?
It's both. So it is an Apache repository. It's an Apache project we're incubating in order to build our community. And the maintainer, the initial committers, you can see them on the webpage. There's a bunch of people from Google, because it kind of came out of Dataflow, but what we really want is for this programming model to include everybody. So a lot of our committers are from data artisans. So the authors of Flink are also the authors of the Beam Flink translation layer. And there's a Spark runner, and it's maintained by kind of a variety of people from different companies. I only like to say like what people have GitHub badges for, so I'm not speaking for any company, but there's definitely a lot of significant companies like Twitter and Spotify and whatnot that have contributed, if you just look at badges. Yeah.
When you talk about the batch model and the streaming model, can you show an intermediate model where you have 6 files coming in and
Yes, so the question was, you talk about batch model and streaming model, and is there sort of an intermediate model where you have sort of files coming in? And I would say that so Beam is a unified model. So there's bounded data, which could be logs, it just means you know it ends, and there's unbounded data where it'll never end. So what you've just described is definitely unbounded data, right? You've got logs, they're rotating. It's sort of a really bursty stream, right? And so the actual data sources in Beam are also user-defined functions, so that's how I would implement that. It's not currently in there. You could either do it that way, or you could have something that's just tailing the logs into pub sub.
Something like a notification trigger? How do you deal with this?
Well, the bursty part, so if you're a consumer of this unbounded collection, by the time you're consuming it, like you don't have to think about necessarily where it came from, and then you just process it as any unbounded collection, and each runner will have its own performance characteristics, right, as to whether you can kind of scale up the number of workers and scale it down and how you manage that. That's sort of out of band. Does that make sense? Or, yeah. Okay. Cool. If you have any more questions, just find me anywhere. I love to talk about Beam.
All right, thanks, Ken.
Yeah.